All right, next problem says list all the possible rational roots of the function. So this is the rational root theorem we had, which you take the factors of the last coefficient divided by the factors of the first. All right, so if we're going to list the rational zeros of this, the rational zero theorem tells us that the factors of 133, which is not hard to find if you just take your calculator out and start dividing by numbers, 2, 3, 4, you find out that the factors are 7 and 19. And obviously 133 and 1 are always there as well. So you take the fraction of these factors divided by factors of the first coefficient, which is just 1 and 7. So all the possible scenarios would be 133 over 7, you have 133 over 1, you have 19 over 7, you have 19 over 1, you have 7 over 7, and 7 over 1, and you have 1 over 7 and 1 over 1. Now I have to do plus or minus for each of these. And actually, some of these simplify too. 133 over 7 is 19, which is right here. 19 over 1 is already there. So I'll get rid of one of those. 7 over 7 is just 1, but that's right here as well, so I'll get rid of that one. I'll simplify this to just 7, and this to just 133. All right, so we've got 1, 2, 3, 4, 5, 6, but there's plus or minus, that's 12 total, which looks like that's good. That's what we need. All right, so we got to do it wants us to list them in increasing order. So the smallest one's going to be negative 133, which makes the largest one 133. All right, and then next we have negative 19, and then that'd be positive 19 for the next largest one. Gets rid of that one. And then 7 would be the way to go next. And then 19 over 7 is just over 2, so it's bigger than these numbers. So negative 19 over 7 and positive 19 over 7. And then we've got 1 would be next, negative 1 and positive 1, and then negative 1/7 and positive 1/7 would be last. Now the question is, are these roots? I think the easiest way probably is to just graph these and find out what they are. That's probably the quickest way. So if you do graph this, you'll notice that it's 4th degree, so it's general U shape. It opens up and it's shifted way up. So you might have to scroll out a bit, but you can see this thing it doesn't have any rational zeros. It must be actually all the zeros are imaginary for this polynomial. So I would have to say no for each one of these. I know it's a lot to type in, but that should be the right answer for this one. All right, the next one then says find all the real zeros of this polynomial. Once again, I could use the rational zeros theorem to do 12 over 1, 6 over 1, right? I don't need to write the 1, which is nice when the first coefficient's 1. 4, 3, and 1. So those are plus or minus. Those places are places where there could be rational zeros. And I could test those to see which ones are rational and do all that. But it doesn't say how I want to do this one, so since it doesn't say, I will go ahead and just do this one from here. Negative 4, negative 1, 1, and 3. Okay? If I want you to do on the test, if I want you to find these, I'll pick a problem that says that, and then I'll make sure I check your work if I want you to find these by hand. You know what I mean? And you can still use the graph to see which one you want to test. You know what I mean? But I want to see some work to show that you've then, from that point, did the synthetic division to get the non-rational zeros. And so we'll do more problems like that, obviously. Kind of like this one. It says that is x plus 1 a factor of this? Well, this is a simple one to check if this is a factor, because this is x minus negative 1. We always do, the factors are always x minus k. And so k in this case is negative 1. So what I'm checking to see if negative 1, when I plug in negative 1 in here, is that a 0? And that makes sense, right? Because if this is a factor, when you plug in negative 1, this would be 0. 0 times anything gives you 0. So I'm checking negative 1 in here. Negative 1 to the even power is positive 1. Negative 1 to an odd power is a negative 1. Negative 1 to an even power is a positive 1. Negative 1 times 6 is negative 6 plus 9. So this 9 would cancel with that 9. Negative 6 and negative 6 make negative 12. Plus negative 9, that's negative 21. So no, that's not a 0 for me. what that means is actually is when I divide x plus 1 into this polynomial, I get a remainder of negative 21. Okay, next problem. If the polynomial f of x has a remainder of negative 2 when divided by x minus 5, what is f of 5? Well, that's just negative 2. Like we just did. It's the same type of problem we just did in the last one. That's the remainder theorem, right? When you divide this k value or this 0 into the polynomial f of x, what you get is the remainder. So when you put 5 into the polynomial, you get the remainder. That's the remainder theorem. All right. This one says use synthetic division to show that x equals negative 2 is the root of this equation. Use the results to factor the polynomial completely. Okay, so x equals negative 2. If it's a root, then I should be able to divide it synthetically into this polynomial 1, negative 6, negative 36, negative 40. And I should get no remainder. So I'm going to drop down to 1 and multiply. Negative 36 and 16 is negative 10. I'm going to add those together. Negative 20, sorry. Multiply and you get positive 40 and there's no remainder. So what that means is this thing factored into x plus 2 was the factor for negative 2. And then what's left over then is a quadratic, which is x squared minus 8x minus 20. All right, and then obviously try to factor these. If they're rational zeros, if there's two more rational zeros, this will factor. If they're irrational, it won't. And obviously if they're imaginary, it won't either. So x minus 10, x plus 2 gives us the right factorization. So that's what they want. And it doesn't matter. I guess order doesn't matter here. So you just got to enter this in right here. Right there. Okay, the next one then, or the last one, gives us this third degree polynomial. Wants to factor into linear and irreducible quadratic factors with real coefficients, so it'll look like this. I need to find, there is a real zero then, obviously, from this factor right here. I need to find what that is. Like, we could obviously do, 10 over 1, 5 over 1, 2 over 1, and 1 over 1, plus or minus. It's one of those. It's got to be one of these, right? So those are the possible rational zeros. Best way is just graph it real quick, and it's negative 2. It ends up being the negative of the 2. So that'd be the factor then would be x plus 2. And I don't know what's left over, but I know it's an irreducible quadratic because they told me that. So I'm going to divide the negative 2 into the polynomial 1, 4, 9, 10 using synthetic division and find out what it is. It'll be negative 2. When you add, you get 2. Gives me negative 4. When you add, you get 5. It gives me negative 10. There's no remainder. So this would be x squared plus 2x plus 5. And they want A, which is 2 in my case. They want B, which is 2 in my case. And they want C, which is 5. Okay, hope this is helpful.